But like all my credits from my research expired in the
Okay, well, it's the program, like 3 months or so.
Yeah. It's just perception and like
Perception.
yeah. The thing is that you need to use dictionaries because we have 30 So my perception I'm already using. Or like it uses dumb dictionaries. It's just an array with like only the values that have one and they have pairs. So the index and the value. So it's like a self-implemented.
I think that was my department. Yeah, I just had this part. Not my other part.
Yeah, no. I should get the one.
Yeah, no place for made like 2 years. And no place really fast. Go back, see calls down.
Alright, so maybe we should start even though it's quite empty today, but I guess this is the price you pay for announcing that what you cover won't be in the syllabus. So, but anyway, so let's start. So the topic of today is what I call, I think unreliable computation is a bad name. I think it should be reliable computation under unreliable circumstances. So we'll see what that means. Okay, so that's the goal of today. Okay, so quick announcements which all of you hopefully know. So only I think 4 or 5 groups have so far sent me this midway write-up, and you really should send me this thing by the end of the week if you want some feedback on your project. Okay, so as I said, this is optional, but I mean if you don't want surprises later, then you should actually do this. Okay, so as discussed in our group meetings. Okay, so all right, and also the makeup homework is out. So again, this also is optional, so it will replace the worst of the previous homeworks. Okay. And yeah, so this is makeup, and this is due 2 Wednesdays from now. Okay, so it's the week of December 13th or something. It's an exam week, but it's a makeup homework, so that's what it is. And it has a bunch of questions about linear programs, about flows, and so on. Okay, so if you remember, flows have not been covered in any of the previous homeworks, so that's part of the reason. Okay. So, all right. So and also the project deadline. So many of you were uncomfortable with the Monday, so I've extended that to Friday, December 15th. Okay, so I think I told this informally to a few of you who asked, but this is just an announcement. Okay, so the project deadline is this, and we spoke about what you need to submit and so on. So, any questions on these so far?
When can homework flow rates?
Yeah, so you'll have to ask the TAs. So I have asked them to submit it by Monday, so hopefully they'll do it. Yeah, so yeah. Yeah, so that's realistically what can happen, because I don't think much has been graded so far, so that's realistically when they will be able to do it. Alright, so the other thing which I forgot to put here is that next week, so we'll do some brief review. Okay, so on Tuesday I want to cover a few new things, but half of Tuesday and most of Thursday and all of Thursday will basically be review for the course. So if you have questions on, if you have like a few homework problems that you want me to discuss or anything generally about the course, you should just feel free to come up with questions. Okay? And it's useful if you, especially for these homework things, if you write to me beforehand, so that I can, I can kind of compile a list of things beforehand. Okay, so if you have specific questions, just send email. Okay, so all right. So any other concerns, questions? All right. Okay, so last lecture we started looking at this interesting notion of online algorithms, right? So the idea there was you've got to make decisions as we go, so you don't know the full input for the problem. Okay? And so the kind of examples we said were renting versus buying skis, okay? Or you could also think of like buying a season pass versus buying each time or something like this. We also saw this very simple example of finding a restaurant on a line, okay, where we saw that doing some kind of a repeated back and forth is the best way to do it. And a more serious example we saw was caching pages, right? So this is how memory caches operate. And in general, in all of these problems, the goal is to compete with the best optimum in hindsight. Okay, with the optimal solution in hindsight. Okay, so your algorithm will have some cost, and we said that this is known as the competitive ratio of the algorithm. And this is defined as cost of algorithm divided by the cost of opt in hindsight. And as usual, this is worst case over all inputs, right? So this is max over all inputs, all possible inputs. Okay, so this is how we define the competitive ratio of an online algorithm, right? So this is so in some sense you want your algorithm, which has no idea about the future, to be able to compete with the optimal algorithm in hindsight. So that's the idea here. And we saw a few examples of this for renting versus buying. We said that you can always compete, have a ratio of 2. Okay, so at most a factor 2. And here we saw that it was at most a factor of 7 or something like this. Okay. So this is what we saw last time. All right, and about caching, we spent quite a bit of time on this, and we said that sometimes it's actually difficult to come up with algorithms with good competitive ratio. Okay, so what we said is that if you have a cache of size k, okay, so if you have a cache that can hold up to k pages, okay, so remember this was the parameter. And we said that no deterministic algorithm for caching can have a competitive ratio that's better than k. And I didn't actually prove this. I proved this only for LRU, but I actually stated this here. Right? So this is what we did. Okay, so, and this is a rather negative fact, right? Because it says that nothing very interesting can be done for for caching. Okay. And then we saw that there is this popular algorithm in practice, which is the least recently used. So this is just a way to deciding which page to evict. Okay. And this is something that people commonly use in practice, and we said that this actually achieves a competitive ratio of k. Okay, so least recently used is in some sense the best possible, okay, because no deterministic algorithm can do better than k, and this one actually achieves a ratio of k. Okay, so this, and what that means is that the number of cache misses that LRU has is at most k times the optimal number of cache misses that are possible. Okay. So, and we saw a proof which was a bit intricate. So, any broad questions? Okay, so this is, yeah, all right. So one thing I wanted to state about LRU, which we didn't have time last time, for which I'll also put up a link if you're interested in more details. I just wanted to state this thing is so the factor of k that we saw in the previous slide, right? So it looks really bad in some sense because k in practice can be huge, right? So you can probably store like a few thousand pages in memory. Okay, and a factor of 1000 comparative ratio sounds really bad. Okay, so the question is there any formal way of saying that it's not so bad in practice? Okay. And this is something that I'll talk briefly about next class. So this is called beyond. So this is this pretty broad area of research, and it's called beyond worst case analysis. Okay, so the idea is that you want to make some assumptions on the inputs and you want to get better guarantees. Okay, and so it turns out that you can say the following about LRU. Okay, so suppose you have an input sequence. Okay, so remember, input sequence is basically a list of requests for different pages, right? So if you have an input sequence where the optimum for a cache of size k is not too far from the optimum for a cache of size k by 2. So you expect this to happen, right? So if I have a cache of size k and I have some optimum number of misses, okay. Now if I had a cache which is a little bit smaller, okay, so k by 2 or 3k by 4, doesn't matter. So what would you expect the number of cache misses to be? Firstly, would it be higher or lower than opt? Would be higher because, and why?
Because there's less spaces.
Yeah, there's less space, so you expect that that this would be small, right? So, okay, so you expect something more than opt, and what we are saying is that this is not too much more than opt. Okay, so let's say this is at most some 2 times opt. Yeah, maybe 2 is too optimistic, so let's do 4 times opt. So if you had such an assumption where the optimum of k by 2 and the optimum for cache of size k are kind of close to one another, then you can actually prove that LRU gives a constant comparative ratio. Okay, and that's what this theorem captures. Okay, so the numbers are not so important, and I will give a link to, I mean, if you're interested in the proof, a link on the course page. But the message here is what is actually important. So what it's saying is that if you had a request sequence which is kind of robust to the cache size, okay, so in the sense that if you double the cache size or if you halve the cache size, the number of cache misses don't go off too widely. Okay, so if you had a request sequence like this, then LRU is actually really good. Okay, so it's just a constant that's independent of k. So, point to note is that this is a constant independent of k. And trying to come up with assumptions like this, which seem natural on real life inputs, is this area called beyond worst case analysis. Okay, so we'll talk a little bit about that next time. Okay, so any question on the statement of this result? Because this is, I mean, yeah, it's non-standard if you're seeing this for the first time. So. Okay, so anyway, so let's, so we'll stop caching here and let's try to move on to the main topic of the day. So this is something I wanted to mention about LRU, that even though what we can prove in the worst case is bad, we usually don't expect it to be like a factor k. Alright, so what's the goal for today? So the goal is, so I want to talk briefly about how you do computation when you have some noise in the computation itself. Okay, so far, and typically in algorithms, you assume that everything is flawless, right? So when you ask for something, you get what you want. Okay. Now the question is, can you do something where you have some noise And these kind of things are common, right? Like some circuits could break, communications could fail, and things like this. Okay, so you could have somebody who's actively being adversarial. Okay. And the question is, can you do interesting computation even in such situations? So that's the general goal for today, and we'll do this with a very simple example. So we'll do it in kind of using a puzzle. So, and okay, let's start with a very basic one. Okay, so suppose I pick a number between 1 and a million, and I ask you, and you're allowed to ask me 20 questions. Will you be able to guess what, or will you be able to find out what I'm thinking? Suppose I answer everything truthfully. So, how would you do this? And why do you say that?
I guess if it was just yes or no, maybe not 20 questions, but if you told if I was low or high, then we could do a binary search by just guessing at the
So I guess okay, I need to clarify what a question is, right? So what are you allowed to ask? So what he's saying is that if I could ask questions like, is your number less than something or bigger than something, then he could do binary search, right? And of course, these 1 and a million were chosen carefully so that a million is close to 2 to the 20. So that's the other thing. So this is why, suppose you were allowed to ask 20 questions, you can always say, okay, your number lies between 1 and 2 to the 20. And now you could always do the usual binary search. You can say, ask if the number I've guessed is less than this or bigger than this, and so on. Okay. So this, in general, if you have numbers between 1 and n, you can do something like log n pairs. Okay. And this is, and the questions you're asking, so this is important because we'll come back to this, okay, are things like, okay, so is the number less than some x? Okay, so we only ask less than or bigger than x. Okay, so more generally, is it in some interval? All right. So this is very basic, right? So we all know how to do this. So now, what if I'm allowed to lie, but I'm allowed to lie in a limited sense? Okay, so that's the question we want to ask. Okay, so this general question is called Ulam's liar game. So it was proposed by Ulam at some point, and so it turns out that these kind of questions are useful to model noisy computation in general. Okay, so there is this whole work by Peter Gatz at BU, and what he does is, he has a book on this thing where you can build these kind of intuitions into circuits. Okay, so these kind of noise tolerant stuff into circuits. Okay, so it's actually pretty interesting. So I'll have a link to this on the course page. But we are going to look at just the puzzle version of this. Okay, so and this is what's called the Ulam's liar game. And one thing you'll notice right away is that if I have no bound on how much I'm allowed to lie, then there's no hope, right? Because you will not be able to figure out what I'm trying to say. Okay, so you've got to make some assumptions on the number of lies. Okay. So the first thing we're going to look at is just have an absolute bound on the number of lies. And the next thing we'll look at is, what if I'm allowed to lie like 20% of the time, something like that. Okay, so both are reasonable assumptions. So let's start with this one. So I tell you that there is some number q, think of, let's say, q equals 2. And I'm going to tell you that throughout the process of questioning, I'm going to lie at most q times. So now, how would you solve this problem? So if I told you that the number of lies is at most 2. So what would be an easy way to extend binary search?
Ask every question 3 times.
Anybody else? Sorry?
Ask each question 2 times.
How many times?
2 times.
Q times. Okay. So what you're saying is, but you still want to ask the same questions, right? As binary search. Okay. So one choice is you can say, okay, I ask the exact same questions like I do in binary search, like is the number less than this or so on. You ask each question Q times. Okay, so why Q? Yeah.
2Q plus 1 if you want error correction, Q plus 1 if you want restore detection.
Okay, so what you can, so Q is a problem, right? I mean, do you see why Q itself is a problem? Because all those could be lies and then you don't know what the right answer is, right? So you've got to ask something like 2 times Q plus 1 as he's saying. So if you ask each question something like 2Q plus 1 times, then you're in good shape because for each question you can take the majority answer. And because the number of lies is at most Q, you get something like the majority answer is always right. Sorry?
I mean, Q and 2 can get the majority answer. No need to Q and 1.
I didn't follow.
I mean, I think it, because there are at most Q lights, so you ask the same question with Q at 2 times. I mean, there should be the two similar answer. We can make that's correct. The other should be different.
Right, so are you saying that you can do fewer than 2Q plus 1? Or,
Yes.
okay, and how are you going to do that? You want to ask exactly Q or something? Or Q plus 2?
Q plus 2.
Oh, you want to ask Q plus 2 questions. Okay, so how does that work? So sure, right? I mean, you will get 2 right answers, but you don't know whether. So suppose in the first step, I ask Q plus 2 times. Okay, whether this is less than this middle point n by 2. Okay. And suppose I get a whole bunch of answers of 0, and I get 2 things. Okay, so Q is, let's say, we were sticking to Q equals 4, let's say. Okay. So now you get. So Q plus 2 is 6, and you have answers like this. Okay. Now, do you know something about, what is the right answer? But you are on the right track, so it does seem like 2Q plus 1 is a waste. But as such, if you want to be able to figure out the right answer at every step, this is what you have to do, right? So what you can do is majority answer. Let's just finish the line of argument that he was saying so that we get some bound. Okay. And that bound is basically that majority answer is always right. So the number of queries total is is 2Q plus 1 times log n. So firstly, does everyone agree with this? So this is easy to say. So now the question is, now let's go along the lines that people are saying. So can you actually improve on this at least a little bit? Okay, so maybe you can go first. Yeah.
Just the number of die that is remain that we can buy.
Okay.
So for example, we can figure out how many lies we have in the first question, and after that, if we say 2 lies, we make Q equal to Q minus 2.
Okay.
And ask 2Q plus 1 question.
Right. Okay. So does everyone see the idea behind what he's saying? So what he's saying is, this is wasteful because, like let's say I asked the first question to q plus 1 times. Okay. And again q was 4, so I'm asking the question 9 times. Okay. And I saw 4 zeros and 5 ones. Okay. Then what I know is that this person has already lied 4 times. So I know that all the subsequent answers are bound to be correct. Okay. So in this case I got lucky, but I could just do one question each next time, and I'm guaranteed that this is true. Okay. So in some sense, one idea here is keep track of number of lies, right? And how would you convert that to an algorithm? So, like suppose, like the first time, okay, so you ask, how many times do you ask and how would you keep track of this? Like, okay, in this case, we were particularly lucky, right? Like the first time there were like Q answers to lies, but yeah, how will you do this more generally, this way of keeping track of stuff?
So the first question you ask 2q plus 1 times.
Okay.
And however many, so for the minority, you have, say, 3 lies. And q, then the next question, q is now 3 less.
Okay, so, but yeah, so that's a very good idea, but the point is that what if there were no lies in the first place, right? Then you're in trouble. Right, so okay, so a bad adversary would save all his lies for the very end. Okay, and then you would be forced to ask 2q plus 1 questions, the same number. Yeah.
So you can sort of stop and answer the question and start thinking in terms of code words and
In terms of what?
code words, and then you make sure.
So we'll get to that. I think you're a couple of steps ahead. Okay, so yeah, any other more natural things along the lines of what he's saying? So it turns out you can actually shave off a factor 2 by doing the kind of analysis that he's saying. Okay, so what you can do is you ask something like q plus 1 questions, okay, initially. Okay, so you start off by asking q plus 1 questions, and or in some sense you ask questions until you get at least q plus 1 answers that are the same. Okay. And then you can show that in some sense you always ask something like q plus 1 times log n. Okay, so this idea can be extended to a little extent, but not by too much. Okay, so the idea here is repeat a question until you get q plus 1 answers that are the same. So here again, a person could save all the lies till the very end, therefore the final, the bound you get is something like this. Okay, so q plus 1 times log n. Okay, so maybe there's a plus q or something like that. Right, so you get a little bit of improvement like this. But yeah, so the question is how you think about this in a more systematic way, right? So the question is, for instance, is this optimal? Right, something like this is the best you can do. So it's clear that you need at least q questions, it's clear that you need at least log n, but you need something like this. So that's what we want to understand today. And so before getting to one of the ways of doing it, so let me tell you a very, so we won't pursue this line of thought, but this is actually a very cute way of thinking about this problem. Okay, and this was due to Joelle Spencer and Peter Winkler. Okay, so I'll tell you about this viewpoint. Okay, so in some sense, this is appealing because it converts this liar problem to a board game, okay, which I think is in a nice sense. So liar problem, where you don't know what is a lie, what is so on, and you can convert it to a full information board game. Okay, so and so this in some sense it also extends the idea that he was proposing. Okay, so in some sense keeping track of how many lies he must that the person must have said. Okay, so that's so that's what we'll see in a bit. But we won't pursue this line of thought. So these guys used this idea to come up with some very nice results about this problem. So, and the idea is the following. Okay, so the idea is, initially, right, so I know that my number lies between 1 and n. Okay, so suppose no questions were asked. Okay, so the information I have is that, or the information you have, the person who's asking the questions has, is any number between 1 and n is likely, it's likely to be the answer. Okay. And what you also know is that the number of lies that have been said so far is 0. So the way these guys put it is that ask me no questions and I'll tell you no lies, right? So that's the starting state. Okay. So that's the initial state. Okay. So this is what we have. And now the question is, suppose you ask a question. So ask a question. So how do we abstractly characterize a question? So that's one of the first things that we should think of, right? So what is an arbitrary question? What does an arbitrary question look like? Like we've been thinking of, oh, is this number less than something? Is this number bigger than something? Right? So can you think of more general questions you would ask?
Is this number odd or even or something?
Yeah, so you could ask, is this number odd or even? Sure. Right. What else? Yeah.
Vector multiplication by the binary that you sort of
Okay, so you could say, is the parity of the binary representation something? Right, so that's what he's saying. So yeah, so you could ask something like that.
You can ask about special, like, is this number a multiple of 11 or 7 or something like this?
So,
To reduce
great, right? So all these are very good things. Is there a way to capture all of these answers in one thing? Sorry?
I mean, also constraint yes or no, binary answer.
Right, so let's say you have binary answers. Okay, so yeah, can you capture? Yeah.
I think I phrased it poorly, but I think that you have a dot product of binary representation of their answer with some arbitrary vector you provide.
Okay.
You can encode, I think, any relevant question.
But you seem to have an abstract notion of any relevant question. What does it mean?
Anything that you could express deterministically as a single bit of information about whatever you're trying to learn about, that's sort of, in this case, the number. I think you can get through vector multiplication with some vector that you provide.
Okay. Sure, but actually there's a much simpler way of thinking about these things. So you could think of any question as, I give you a set and I ask you, does it belong to this set or not? Okay, like anything that you guys said, right? So it's essentially like saying, okay, I give you some set, some subset from 1 through n. Okay, so some subset from 1 through n. So any question is S subset of n, okay, and the question is, does the number. So let's give a name for this hidden number that we don't know. Let's call it h. Okay, h for the hidden number that we don't know. Okay, so does h belong to S? Okay, so any question you can think of as just this, right? And as you can easily see, I mean, this is the most general question you can have, right? It's just a subset, so you ask if it's in the set or not. All right, so you ask this question, okay? Now, what I want to imagine is, so in some sense, suppose the person, suppose I answer, I am the person with this hidden number h, and suppose I answer yes. Okay? So say the answer is yes. So then, what do you, as the person who is doing the querying, know? Like this is the first time you're ever asking this question, right? So the first query is yes, and my answer is yes. So what do you as a person who's querying know?
The next personal answers can be only from that set. So, okay.
So that is if I have not lied, right?
Okay.
So what you know is that one of two things is true, right? So either it was a lie, and H does not belong to S, or you know that H is in S, right? So this is the obvious thing, right? So this is what you know. But now, is there a nice way to represent this answer? And this is what these guys came up with. Okay, so it's a bit tricky, so I will show it to you. So what these guys came up with is to represent this thing as a nice, in terms of a grid. Okay. So what they do is, so you think of initial state is, you have a bunch of options. So think of cards that have numbers 1, 2 through n. And the observation is that, suppose I ask, does H belong to, I don't know, one of these three numbers, to a set consisting of these three numbers. And also, the reason I wrote this in the vertical line is that this is assuming number of lies equals 0. Okay, so at this point, no questions have been asked, so I know that the number of lies is 0. So now what you can say is that suppose you ask these three. Now, if the right answer, if H was within one of those three, and I've answered yes, then what they're going to do is, so let me put it in a different way. So suppose my answer is yes. Okay. So I have said that H belongs to one of these three. Then what I said in the previous thing is that either it was a lie and the answer was actually not in this, or the answer was actually in this, right? So this is what we know. Now, so what this means is that if the true H was let's say this number, then I have lied at least once. Okay. So what you can do is, let's say you push all the numbers that were not in this S to the next level. Okay, push them to the right. So I'm going to define this, actually one other nicer way probably of thinking about it is that if I answer yes to this set, then I push everything else to the right. And in hindsight you can see why this is equivalent to this game. Okay, so let's think about that way. Okay, so this I'm calling it to be number of lies equals 1. And the idea is that if I've answered yes, and my the true H is one of the things that was not in this S, then I must have lied at least once. So that's the meaning of this thing. And if my true age was in the set that was asked, then then I have not lied at all. Okay, so they come up with this kind of a nice board game type representation of this problem, where they say that, okay, so each question is determined by some set S. Okay, and if you answer yes, okay, so if answer is yes, okay, then you can push all the cards not in S by one step forward. Okay. And if the answer is no, you can push all the cards in S. So you can do the same thing in S, one step forward. Okay, so yeah, so I don't know if I should go through an example of this, but especially because we're not going to finish the argument using this kind of viewpoint. Okay, but what these guys achieved is, in some sense, you have a full information board game where at every step somebody comes up with a set S, and you are allowed to either push the set itself or its complement to the right. Okay. And this captures, in some sense, the number of lies you must have said. Okay, so this is a very clever way of accounting. Okay, so this, so I won't go too much into the details of this, but this way of looking at things, it ends up giving something like ends up giving the right bounds for this problem. Okay, but we are going to see a much simpler thing today. Okay, so in case you don't exactly follow this, that's fine. So, all right. But the thing I want you guys to take away from it is that any query can be viewed as a set membership. Okay, so you can ask if this is the. So if I have a bunch of queries S1 through Sm, so I can just view a bunch of M queries as being defined by M different sets. Okay, so this is what we know. And now, suppose I give answers to these queries as 0 means yes, and 1 means yes, and 0 means no. So suppose I say that it does not belong to this, 1 of this belongs to this, and let's say it's 0. Then, so in some sense, can you guys think of ways of coming up with these sets so that from these answers you can actually come up with what the number is, what h is, right? So the goal is, so you can also phrase this problem as given answers in this 0, 1, 3. Can we come up with h? So this is the problem. This is another way to state the same problem, right? And right. Okay, so this is the problem that we want to solve. And I know that at most some of these answers are not the right answer. Okay. So, right. So now let's take a step back and let's again go back to the case where I'm not allowed to lie. So no lies. Okay. So can you give me a set of questions beforehand? Okay. So I'm not. Okay, so the question now is, give me Sm beforehand, whose answers let you come up with age? Fine. So is the question clear? So now I'm restating the problem a little bit, right? So earlier you could ask a question, I'll give an answer, and you could ask a different question and so on. Now I'm asking you to come up with a non-adaptive strategy in some sense. I'm asking you to tell me, can you give me some m sets? Okay, so I want m to be log n again. Okay, so that the answers to these things, if I'm not allowed to lie, will actually let you find age. Any question here? Yeah, so what is that here? So yeah, so this kind of relates to what he was saying. So in some sense, okay. So let me give it. Okay, so the question now is this non-adaptive version. Okay. So what I'm saying here is, can you give me a bunch of sets beforehand so that the answers to these things actually let you find age, right? So let's take a very simple example, right? So suppose I have n being, okay. Now I want you to give me a bunch of sets so that the answers to the set membership queries on these things for these sets, and for now assume I'm being truthful, okay, let you determine what this hidden number is. So what is a trivial way to do this? Sorry? Binary. I mean, so binary search is adaptive, right? So I want you to come up with some set of things beforehand. Okay. You'll see why this is important in a bit. But this is actually, I'm actually saying that something stronger can be done, right? So okay, so I want you to come up with a bunch of sets beforehand, so that answers to these tell you what you come to. We'll see if, yeah. So yeah, what if I allow you to do m equals 5? Can you do this now?
Is your number 1? Is your
Yeah.
number
Okay, so this we all agree is trivial, right? So S1 is 1, S2 is 2, and so on. And if I'm not lying, so this is bound to give me the right. Can you do it m equals 4 in this case?
Yeah, actually you can do m equals to 3 as well. Like,
Okay.
Is your number even? Is it 2? Is it 4?
Okay, so what you're essentially saying is that you ask for 1, 3, 5.
Or, I mean,
Sorry?
okay, I mean, if we consider odd, then 4.
Okay, so we can do something like this, right? So you can ask questions that are very specific like this. Okay, so can you see a way of generalizing this to any n? Yeah.
What's the value for 1's place in binary? What's the value for 2's place in binary? What's the value of etc.?
Okay, so yeah, so that is something you can do in general, right? So suppose I know that the answer lies between 1 and n. You could say, does it belong? So S1 could be set of all numbers in 1 through n that have 0 in their in the first position in binary representation. Okay. So in this example, right? So this is 0, 0, 1, 0, 1, 0. So in some sense, the first set I'm picking is everything that has 0 in the first position. Okay. So I'm picking this, this, and this. And the key thing here is that the answer to this question is going to tell me what the position in the first bit is. Because I'm not lying, right? So if I tell you that the number is not in that set, then I know that the first bit has to be 1. Okay. And so that's the idea here. And S2 could be all the numbers that have 0 in the second position. And the key idea is that the answer to this will tell me what the bit in the second position is. Okay. So this is a somewhat tricky thing, so let me pause for a bit to make sure you all understand. So the point I want to make here is that I can ask only log n queries, because log n is the number of bits in the binary representation. I could ask all these queries beforehand. Okay? So this is different from binary search in the sense that in binary search I ask you a question, look at the answer and then change my query. Right? So this is non-adaptive in that sense. Okay? So I'm asking all these questions beforehand. And I'm still able to tell what the final answer is, assuming there were no lies. Okay. So this, so this is a good fact to know, which is that if we have no lies, so in some sense, the corollary is that if we have no lies, then answers give the binary representation, and which is equivalent to getting what the number is. Okay. So this is, and this is one way in which you can just come up with some bunch of questions beforehand. All right. So now, so is there a different way to choose these S1 through SM? Okay. So now I'm allowed to have lies, right? So let's say I'm allowed to have like Q different lies, and the question I want to ask is there right? So in some sense, what questions should I be asking? Right? So that's what we want to ask. And yeah. So any thoughts? So firstly, is this thing clear? Yeah, if you have no lies, then you can ask all questions before. So now let's restrict to the same case, like all questions have to be asked beforehand. And now let's say I have a small number Q of lies. So now, how do you ask questions? Okay, so is there a natural way to extend something like this?
Ask just the first question, keep this one times.
Okay, so yeah, so you can also extend what we have done before, right? So you are saying that we can do exactly what we did before. So you come up with the same set S1, S through up to SM that you did, that we had over here. And you could say, okay, I ask S1 a bunch of times, and then S2 a bunch of times, SM a bunch of times.
No, but I mean, if we like, is if it is q plus 1 times.
Okay.
If the answers are different for in the q plus 1, so we know that we had covered this number of ways. So it may happen that we don't even need to go, we don't even need to ask SM a bunch of times.
Right, but remember the one of the things that I'm now saying, right? So I want you to give me the sequence of questions beforehand. Okay. While in the actual problem you are allowed to be adaptive, I'm just coming up with, I'm actually going to show that even in this restricted condition you can actually do pretty well. Okay. So that will be my ultimate goal. Okay. But before we get there, so let's assume for now you want all questions beforehand. And now, yeah. So one thing to do could be to ask each thing multiple times. Right? So 2q plus 1 times, same kind of thing you can now say. The first 2q plus 1 questions, by taking the majority, you'll be able to figure out what the first bit is. But yeah, so can you think of now a better way? So in some sense, I guess one way to think about this is, what are the answers to these questions if I had a particular number h? Okay. So suppose I asked this set of questions. Okay, everything appearing 2q plus 1 times. And let's again, for concreteness, think of n being 5 like this. Okay. So n equals 5. So in this case, m equals 3. And I'm asking, in some sense, if the first bit is 0, first bit is 1, and so on. Right? So if the first bit was actually 0, then you would get 0, 0, 0 here. And assume that q is 2, just for concreteness. Okay, so in fact, let's assume q equals 1. Okay, then we are asking each question 3 times. Okay. Then my answers would be, if I were not lying and my actual number h was 2, okay, then my answers would be 0, 0, 0, 1, 1, 1, 0, 0, 0. Okay. So this is if I was not lying. What if I'm allowed to do one lie? How could my answers vary? What could the string that I output, right? How could it look like?
Just one bit flip.
Okay, so one of these bits can get flipped, right? So now I have 9 different bits here. And if I'm allowed one lie, so then okay, so maybe this guy changes to 1, or one of these things gets flipped. And in some sense, so this is if h is 2. So if h is 2, then I have a whole bunch of options, but I know that it's going to be 1 bit away from this string. Okay, so that's a good observation. If my hidden number is 3, then the true representation was this. Okay, so I know that it's going to be 1 bit away from this number. So all right, so it's going to be maybe something this way visible or something. Okay, so in some sense, what we are saying is that every number h, okay, so if you look at all the queries, is being mapped to some string which has bunches of zeros and ones. Okay, and if I'm allowed lies, then essentially I'm changing some bit, a couple of the bits, right? Or if the number of lies is q, I'm allowed to change q of these bits. Okay. So the question is, what is a sequence of questions achieving, right? So if I have a bunch of sets S, one abstract way to think about it is, a sequence of questions essentially maps every number h to some binary string between 0 and 1. 0, 1 to the m, right? So that's that's how we want to think about things. Okay, so if I have a set of queries S1, S2 up to Sm, all it's doing is it's mapping each h in this interval n to a string in 0, 1 to the, and this is the set of answers, okay, the vector of answers. All right. So the first question, right? So even if there were no lies, okay, so now we want to essentially, given a bunch of questions, I want to think of, I mean, in some sense, what is this mapping doing, right? So suppose I know that, okay, so let's take a different example. So suppose I know that S1 is 1, 2, S2 is 1, 2, 3, something like this. So I had something very simple like this. Okay. So all I'm saying is that h equals 1 maps to 1, 1. H equals 2 maps to 1, 1 as well. H equals 3 maps to 0, 1. So now what you can see is that you can kind of see when you can tell apart two numbers, right? So if my true answer was h equals 1, then I would have gotten a sequence of 1, 1 if there were no lies. And if my true answer was 2, I would also have gotten 1, 1. Okay, so if I had asked this S1 and this S2, there's no way of telling apart h equals 1 from h equals 2. Okay. So in some sense, this is the kind of issue that's going on, right? So the questions you ask should at least be able to differentiate every number between 1 and n from every other number. Okay. So this is why I want to think of this mapping as a code. Okay. So think of every h mapping to a code C of h. Okay. And the C is just defined by these sets S. So if you want to have any hope of distinguishing, even if there were no lies, okay, so then C of h1 must not be equal to C of h2 for any h1 not equal to h2. Okay, because otherwise this set of queries will not be able to tell h1 apart from h2. Okay, so it's kind of like this example, right? If my s1 was 1, 2, S2 was 1, 2, 3. Then h equals 1 essentially maps to this 1, 1. H equals 2 also maps to this 1, 1. Okay, so just from the answers to this membership, I won't be able to tell one set from the other, one h from the other. Okay. So this is, yeah, pause for a bit. So some of you look lost. So. Okay, so what I want to say is that any sequence of questions which are given beforehand define a code. Okay, and if I want to be able to recover the original number, then this code must have the property that C of h1 must be not equal to C of h2 for any h1 not equal to h2. Because if the codes are equal, then it's like saying that the answers to all the set memberships are exactly the same. So just from this set membership information, I won't be able to tell h1 apart from h2. Okay, so the answer could be either one. So this is a very simple notion. So I'm going to see if you guys have questions. So all of this is for the case when when there are no lies, right? So far. So now, can you think of what happens when you have lies? Like, I want you to think in terms of this code, right? Like I ask a bunch of questions S1 through Sm. and I get these answers. Okay. And for every number h, now there is this code C of h. And we know that if I lie, then this code essentially changes a little bit, right? So like a few bits of the code get flipped.
So code, even if h1 is not equals to h2, the code might be equals to, and ch1 might be equals to ch2. Because like if the h equals to 1 bits, the first bit get flipped, so it will be 0 1. H equals to 3 also is 0. So essentially, even though they are different,
Yeah.
they might their code might look equal, similar to.
Okay, so what he's saying is that if I define the answers as the code, then like in this case, for instance, just by my right answers could have been these guys, but the answers that I give you could be something like 0 1 0 1. Okay, and then I have lied exactly once, right? And therefore I basically flipped this way. Alright, so is there so suppose I wanted to ensure that something like this doesn't happen, even for the flipped codes, right? So even for the perturbed codes, then, or rather even for this situation with lies, so is there something I can do? So for, again, take a look back at this, right? So the key idea here is to think of the right answers, right? So suppose the right answers, the correct answers, where there were no lies, looked like this. Then I'm able to say that even if I perturb a little bit, perturb one bit, I'm never going to get the same answer. Okay. So, alright. So that's kind of the key observation. Okay, so handling lies is kind of the key idea behind this thing is to think about how the right answers or the true answers to the queries must look like. Okay. So in this situation, the true answers for these two differ by only one bit, right? So in some sense, by flipping one bit, I can make you confused between one or the other. So, is there some way of avoiding this?
So if there are q lies, we can add q bits extra to answer and some kind of parity check.
Okay, so right, so that's kind of where we want to go, right? But what is the idea behind your answer? So why do you think that adding some parity checks would help?
Like for example here, in this case, we can lie one time.
Yes.
So it means there was anyway only one bit difference between the true answer and the other answers.
Okay.
So if we add one more bit like, okay now.
I mean, you guys are on the right track, right? So, that makes some sense. But can you abstractly state what nice property, would ensure that you don't confuse between things even after some lies?
You can find a distance between two code words based on the position to differ, and then make sure your set of code words doesn't include any two that are beneath some distance.
And what do you mean by code word now?
Any C of H1 for me.
And basically their XOR should not be equal to 0 time they are put up with something like that.
Well, that's true in here, right? So,
but if we
so what essentially what do we want, right? So this is a very simple thing. So let's write down what we want. Okay. So if the true, the idea is you have to think about how the true answers to these queries look like, right? So let's call the true answers. Let's give it a slightly different name. Okay, so the true answers, let's call it T of H. Okay, so this is the set of true answers. And what we know is that the code that we get, or rather the set of answers that we get with lies, okay, C of H is, this is with lies. Okay, is T of H plus minus some q bits of noise. Okay. And right, so what we want is C of H1 is not equal to C of H2. So how do we ensure that, I mean, what nice property of the T's would ensure that something like this does? This is now a very geometric question, right? So do you guys see what you mean? Like in some sense, if the T of, let's say T of H1 was 0, 0, 0 and T of H2 was 1, 1, 1, then with one lie, there's no way these two can then be equal. So what property would you like for the T's? That's one thing you want to ask.
They should differ by at least qubits.
Okay, they should differ by at least q. Okay, fine. But now 0, 0, 0, 0, 0, 1 differ by q bits, right? But when you perturb them, yeah.
Differ by q plus 1 for error detection, or I think just 2q for error correction.
Okay, so let's, I mean, in your language we want error correction, okay, so, but we haven't defined these things, so let's just, I mean, what do we want here, right? Like you want, even after perturbing things, you don't want two different H's to have the same code, okay? So if I think of it geometrically, right, so T of H1 is some point in space, okay, T of H2 is some other point, okay? And even after moving a little bit here, and even after this is moved to some other point here, you don't want them to map to the same point. So, and each point is essentially moved a distance of q when you are thinking of 0, 1 to the m. Right, so you're changing m bits. You're changing q bits. Okay, so you have some m bit string. Okay, and you're changing q of these bits. Okay, so you have 0, 1 through the m, some point in 0, 1 to the m. And you're changing q of those bits, you're getting some new point. And this one you're changing q of these bits. Okay. So if you ensure that these two differ in at least 2q plus 1 bits, then there's no way perturbing one by q bits and the other by 2 by q bits is going to lead to the same thing. Okay, so is this notion clear? So the claim is, if T of H1 and T of H2 differ in at least 2q plus 1 bits, then C of H1 is never equal to C of H2. Okay, no matter how we perturb things. So is this clear to everybody? Okay, so right, so this is actually a very simple claim, and it's true by essentially by triangle inequality, right? Because if I perturb this one by h and this two by h, and if there were this one by q, this one by q, and they were 2q plus 1 apart, then you can't get to the same point. So this is a very simple reasoning. Alright, so now the question is, remember the T's were supposed to be the true answers to the set of queries. And we haven't even come up with the set of queries, right? So we said that the queries must be such that the true answers for any two numbers differ by a lot. Okay, so that's the connection to coding theory, and so this is where this leads us to this notion of error correcting codes. So error correcting codes are essentially ways of achieving this precise thing. Okay, so what do I mean by that? So code on a domain of size n. Okay. With m bits on a domain of size n with yeah, let's just introduce a notation. So this is not standard notation, but with distance d. Okay, so this is a mapping from n into 0, 1 to the n. Okay, so let's call this mapping T again, just to keep consistent with the previous thing. So an error correcting code with m bits on a domain of size n, distance T is a mapping such that. So this is essentially, this is basically the set 1 through n. So you have a mapping T that maps any number to 0, 1, 3 m. Okay, to an m-bit string such that T of I, the distance between T of I minus T of j is bigger than or equal to T for all I not equal to j. Okay, so this is what an error correcting code is. Okay, so you have a domain of size n. You want to map it to strings of length m, with the property that the codes for any two different numbers differ in at least d bits. And what this previous thing says is that in some sense, if I had an error correcting code with d being equal to 2q plus 1, okay. So the connection to the earlier thing, connection to liar problem is that an error correcting code with d equals 2q plus 1 and again some n leads to a strategy with m questions. Okay, so what it's saying is that, so this is so this is what we have essentially established, right? So but it requires a little bit of proof. So is this claim clear to everybody? So I want to say that suppose there exists an error correcting code and it has d equals 2q plus 1. I'm not asking you what this code is at this point. Okay, suppose there exists some code with d equals 2q plus 1 and some particular value of m. Okay, and this is for the domain 1 through n as before. And this leads to a strategy for this liar problem with at most n questions. So why is this? Roof. Sorry? Sorry? Yeah, so it is triangle inequality, but what are the questions? Like, so far I'm just telling you there is some error correcting code, right? So, what are the questions you would ask? What are the SIs? So earlier, I'm asking you the reverse question, right? So earlier I told you what the SIs were. SIs were defining some code, okay? And I wanted some property of the code. Now I'm telling you, here is a code which has this nice property that you wanted. Okay? What are the questions, SIs, that you're going to ask?
What are the,
Sorry?
I didn't quite get the question. What are the what?
No, so I'm asking the reverse question. Like earlier we said that, actually maybe it's better to talk. Okay, so earlier we were saying that you had some questions, we were coming up with the code. Right? Now I'm telling you, suppose I gave you some error correcting code, how do you construct the questions from it? This is what I'm asking here. I mean, we saw the connection, but I just want you guys to be aware of it, right? So, yeah?
So some codes, not all, you can phrase as a matrix multiplication.
Okay, but why?
So you
No, I'm not asking you how you construct error correcting codes, right? I'm just telling you, suppose I gave you an error correcting code, which has this property that the distance is at least 2q plus 1. Okay. Now, going back to our problem, what questions would you ask? Like, questions are basically some subsets that you could ask, right? So what would be the first question, for example? This is actually... Okay, so since we are out of time, I should probably just say, so the questions we ask are basically, they come from this connection, right? So we've got to ask, you look at the code, okay? A bunch of numbers from 1 through n are going to have 0 in their first bit. Okay? So you build S1 to be set of all I in this n, such that T of I has 0 in the first bit. And you just ask, right? So or let's say it has 1 in the first bit, and you ask if your element h belongs to this S1. And if it was the right answer, then you would get the first bit. Otherwise, you would get a corrupted version of the first one. So this is basically the connection, right? So this is why, suppose I gave you some error correcting code that has d equals 2q plus 1, you can actually come up with a good set of questions. Okay? And this is the connection between error correcting codes and this liar game. Okay? And it turns out liar games have connections to noisy computation and things like this. Okay, so that we'll briefly finish it up next class, but this is the basic connection to error correcting codes. I also wanted to show you how you construct these codes. It's actually pretty simple, but since we don't have time, I'll just have a small link to the PDF.